Welcome back students to second part of the chapter work energy and power topic collisions. In our previous session on this topic we had discussed about the different types of collisions. I told you that in elastic collision momentum and kinetic energy are conserved. Perfectly elastic collisions occur on a microscopic level. In macroscopic collisions only approximately elastic collisions actually occur. While in an inelastic collision, kinetic energy is not conserved, although momentum is still conserved. Now, if the objects stick together after the collision, it is a perfectly inelastic collision. Let's straight away get to the topic of discussion for today, elastic collision in two dimensions. Let us consider two perfectly elastic bodies A and B of masses m1 and m2 moving along the same straight line, say x-axis, with velocities u1 and u2 respectively. If the body A is moving with a velocity greater than that of B, that is, if u1 is greater than u2, then two bodies will collide. After the collision, the two bodies A and B move with velocities v1 and v2 along the directions, making angles theta and phi with the incident direction x-axis, as you can see in the figure. Now, since the collision is perfectly elastic, the kinetic energy must be conserved. Therefore, we can write half m1 u1 square plus half m2 u2 square equal to half m1 v1 square plus half m2 v2 square. Let's mark it as equation 1. Now momentum is a vector quantity. As the two bodies move along different directions after the collision, the momentum of the two bodies is separately conserved along x-axis and y-axis. So, the component of momentum of body A, component of momentum of A after collision along x-axis, that is equal to m1 v1 cos of theta. Similarly, component of momentum of B after collision along x axis will be equal to m2 v2 cos of phi. Now applying law of conservation of momentum along x axis, we have m1 u1 plus m2 u2 equal to m1 v1 cos of theta plus m2 v2 cos of phi. Let's mark it as equation number 2. Similarly, we can write down for the component of momentum of A along y-axis to be equal to m1 v1 sine of theta, and for B it is equal to m2 v2 sine of phi, this will be along OY dash, and so along OY it should be equal to M2 V2 sine of phi with a minus sign. Now, before collision, the component of momentum of body A or of body B along y-axis is 0. There was no movement along the y-axis. So, the total momentum along the y-axis initially before the collision has to be 0. So, applying law of conservation of momentum along y-axis, we can write down initial total momentum was 0, and that is equal to m1 v1 sine of theta minus m2 v2 sine of phi. So therefore we can write down m1 v1 sine of theta to be equal to m2 v2 sine of phi. Let us mark it as equation number 3. Now in the study of collision between two bodies, we have to find the values of 4 parameters. What are those parameters? V1, V2, theta and phi. Now since these 4 parameters are connected by only 3 equations, what are those 3 equations? Let's go back a little bit. So you can see this was equation number 1. This is equation number 2. And this is equation number 3. So using these 3 equations, the values of all the 4 variables cannot be found. In practice, either the angle theta or phi is measured experimentally. Knowing, suppose say theta experimentally, the values of v1, v2 and phi can be found in terms of u1 and u2 and theta by using these 3 equations. Now let us discuss some special cases. Let us find the values of v1, v2 and phi in the case when the target body B is at rest. So we can put u2 to be equal to 0. And let us assume that the mass of the two colliding bodies are same. So this means m1 is equal to m2. Let us say it is equal to m. So we are considering a situation when collision is taking place between two bodies of equal masses and the target body is at rest. So now we can substitute these values in the 3 equations that we have obtained earlier, and then we will get u1 square equal to v1 square plus v2 square. Then u1 equal to v1 cos of theta plus v2 cos of phi, and v1 sin theta equal to v2 sine of phi. So these are the 3 equations that we can obtain. Now these 3 equations can be slightly rearranged and written as u1 square minus v1 square equal to v2 square, u1 minus v1 cos of theta equal to v2 cos of phi, and obviously the third equation remains as it is. So let us mark them as equation number 1, 2 and 3 again. Now squaring and adding equation number 2 and 3, we get u1 minus v1 cos of theta whole square plus v1 sin theta whole square equal to v2 cos of phi whole square plus v2 sin of phi whole square. So let's do the expansion. We will get u1 square plus v1 square cos square theta minus 2 u1 v1 cos of theta plus v1 square sin square theta equal to v2 square cos square phi plus v2 square sin square phi. So we can write down u1 square plus v1 square taking as common cos square theta plus sin square theta minus 2 u1 v1 cos of theta equal to v2 square, and again we can take it out as common cos square phi plus sin square phi. So we get, using the trigonometric identity, that cos square theta plus sin square theta is equal to 1. So we get u1 square plus v1 square minus 2 u1 v1 cos of theta equal to v1 square. Let's mark it as equation number 4. Now going back to equation number 1, we had u1 square minus v1 square equal to v2 square. So now we can write down u1 square plus v1 square minus 2 u1 v1 cos of theta equal to u1 square minus v1 square. This is actually v2. So as you can see that we can cancel the term u1 square from both the sides. So hence we get twice of v1 square equal to twice of u1 v1 cos of theta. So 2 and 2 gets cancelled. You can cancel out 1 v1. So therefore v1 is equal to u1 cos of theta. Let's mark it as equation number 5. Now on substituting, we had an equation u1 minus v1 cos theta equal to v2 cos of phi. So now we can write down u1 square minus u1 cos of theta square equal to v2 square. So v2 square is equal to u1 square. 1 minus cos square theta can be taken out as common, and that is equal to u1 square sin square theta. So we get v2 equal to u1 sin of theta. Let's mark it as equation number 6. As v1 sin theta is equal to v2 sin phi. So we can write down, in place of v1 we can write down u1 cos theta into sine of theta is equal to u1 sine theta into sine of phi. So hence you can see that we get cos of theta equal to sine of phi. So now we can write down sine of phi equal to sine of 90 minus theta, because we know that cos theta is sine of 90 degree minus theta. Therefore we get phi equal to 90 degree minus theta, or we can write down theta plus phi equal to 90 degree. This means that if a body collides with the target body of equal mass at rest, the two bodies move at right angles to each other after the collision. Let us come to the next topic, inelastic collision in one dimension. We have already studied that the collision in which momentum is conserved with some loss in kinetic energy and the colliding bodies continue to move along the same straight line after the collision is called an inelastic collision in one dimension. So let us consider two bodies A and B of masses m1 and m2 moving along the same straight line with velocities u1 and u2 respectively. The two bodies undergo head-on collision and continue moving along the same straight line with velocities v1 and v2. As it is an inelastic collision, so momentum is conserved. So we can write down m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. Now in an inelastic collision, the velocity of separation v2 minus v1 is smaller than the velocity of approach u1 minus u2. So coefficient of restitution is given by v2 minus v1 by u1 minus u2. So we can write down v2 to be equal to v1 plus e times u1 minus u2 from this formula. Let us substitute this expression for v2 in the above formula. So we get m1 u1 plus m2 u2 equal to m1 v1 plus m2, and in place of v2 we can write down v1 plus e times u1 minus u2. So on further substitution we get m1 plus m2 times v1 equal to m1 minus e times m2 u1 plus 1 plus e times m2 u2. Therefore v1 is equal to m1 minus e m2 u1 plus 1 plus e times m2 u2 divided by m1 plus m2. Similarly, by eliminating v1 from this equation, we can obtain an expression for v2 as m2 minus e times m1 u2 plus 1 plus e times m1 u1 divided by m1 plus m2. These equations can be used to find the final velocities of the two bodies after collision when the collision is elastic or perfectly inelastic in nature. So for perfectly inelastic collision, E is equal to 0. So therefore we get v1 equal to m1 u1 plus m2 u2 divided by m1 plus m2, and v2 is obtained as m1 u1 plus m2 u2 by m1 plus m2. This means v1 is equal to v2 for perfectly inelastic collision in one dimension. So both the bodies after collision move with same velocity. That implies that the two bodies stick together. Now if m1 is equal to m2 and that is equal to m, then v1 will be equal to m minus e times m to u1 plus 1 plus e times m u2 divided by m plus m. So that gives us v1 to be equal to 1 minus e times u1 plus 1 plus e times u2 divided by 2. Similarly, we can get v2 to be equal to 1 plus e times u1 plus 1 minus e times u2 divided by 2. Now if u2 is equal to 0, then we get v1 to be equal to m1 minus e times m2 divided by m1 plus m2 times u1, and v2 to be equal to 1 plus e times m1 by m1 plus m2 times u1. So again, if m1 equal to m2 equal to m, so v1 is equal to 1 minus e by 2 times u1 and v2 is equal to 1 plus e by 2 times u1. Now if the mass of the target body is negligible as compared to the incident body, that is for m2 much smaller than m1, we have, neglecting the smaller terms, we get v1 equal to u1 and v2 equal to 1 plus e times u1. Similarly, for the incident body having a negligible mass, then neglecting the smaller terms, we get v1 equal to minus e times u1 and v2 to be equal to 1 plus e times m1 divided by m2 into u1, which is approximately equal to 0. We will end our discussion for today at this point.